So we're going to move on to chapter 4, which is all about something called matrices. So we're going to talk about this one specific thing today. What is a matrix? So that would be the singular word for it, a matrix. And then if you have multiple of them, you call them matrices. You don't say matrices. So what is a matrix? And this whole chapter will be dedicated on working with matrices. So what is it? It's just a rectangular arrangement of objects or numbers. This is useful for storing data. And it makes things easier to read as far as an assortment of numbers in a big kind of block. And you'll see what I mean when we look at them. An element is every single object that's in a matrix. So a matrix is made up of elements, individual elements. For example, we have a matrix down here, and I'll go into detail with that a little bit later. So let's read through the example. Below is the median salaries of collegiate head coaches for 3 different sports, based on the highest degree and institution grants. We're going to label the columns and the rows correctly. So if you look at this, I don't know, this is kind of cut off a little bit. Should be little hooks on the bottom. It actually looks like a hook on top and the bottom, kind of like a bracket on both sides. And then you have like a list of numbers, and they're separated into rows and columns. So if we're going to talk about the first row, that would be football. I'm going to label this as the first row, and then we go down from there. So it goes 2, 3. That's how many rows you have. And then you go by the columns going across the top. There's a doctoral column, a master's degree column, you have a bachelor's, and then you have an associate's. So the way you can actually read this is like if you were asked the question, well, how much would a baseball coach earn if he had the bachelor's degree? So you could look for baseball, match up with bachelor's degree, and you'd find, okay, that's $41,000. So that's kind of how you read this. If you know the two things, you can figure out the salary. So it's just a block of data. Every single thing in here is considered an element of the matrix. All right, so the matrix has how many rows and how many columns? There's 1, 2, 3 rows, and there's 4 columns. So normally we represent this by a certain way. So this is called the dimensions of the matrix. Each matrix is represented by first the rows, we call M, and the columns are N. So for example, example 1, they had dimensions 3 rows and 4 columns. And the way you write this is by doing a little X in here. This is the word, I'll write out here, by. So you would say that this matrix is a 3 by 4 matrix. You always do the rows first and then the columns. So the dimension is read as your M, your rows first, by your columns. Oops. So M by N. And just to reiterate, N is the total number of rows in the matrix. N is the total number of columns. So rows always goes first and then columns. So we're just going to practice actually listing out the domains or the dimensions. So let's see. Example 2, write out the dimensions of the following matrices. So if you need to, you can just write them out. So we have 1, 2 rows, 1, 2 columns. This would be a 2 by 2. And you keep going. This has 1 row, but then it also has 3 columns. So it's a 1 by 3. C, 1, 2, 3, 1, 2. So this is a 3 by 2. D has 1, 2, 3, 1 column, 3 by 1. And you keep going through the rest of them. I'm sure you guys can figure it out, hopefully without even actually labeling them. Just fill it in. There's 2 rows, 3 columns, so it's a 2 by 3. 2 rows, 1 column, 2 by 1. 1 row, 2 columns, 1 by 2. And then we have 3 rows, 2 columns. 3 by 2. So you can have any kind of combination of rows and columns, and you just put the X in between them, and that's how you read it. And there, again, they have the hooks on the edges. Example 3. Let matrix K equal this whole entire block here. We have 1, 3, 6, -4, 8, -5, 8, 6, and 1. So how do you find K, X, Y? So if you're trying to look at the matrix and you're trying to identify a specific element, XY means that the X is the row number and the Y value, the one that comes second, is your column number. So again, if we were to label these 1, 2, 3, 1, 2, 3, and we want to go through this, and we were trying to find the following, what's K1, 2? That means you go in the first row, right? That's here. You go down the second column, and wherever they intersect is 3. So the element that's in K of 1, 2 is 3. Now I guess I'll just erase that. That's how you basically identify the elements in the row. So for the next one, K of 2, 1, that would be the second row, so it should be in the middle here, second row, and then first column, so wherever they intersect, which would be -4. And you just keep doing it like that. K of 3, 1, that would be the third row, first column, that would be 8. Keep going. 3, 3 would be third row, third column, which is 1. K of 1, 3 is first row, third column, is 6. And 2, 2 would be right in the middle. That'd be 8. Again, hopefully not too difficult. Okay, so now we're actually going to try to fill in a matrix that's already kind of made for us in example 4. So write the following information in matrix form, which is already written out for us. According to the Statistical Abstract of the U.S., in 1980, approximately 3.5 million males and 1.9 million females participated in high school athletic programs. 10 years later, 3.4 million males and 1.9 million females participated. And so that would be 1990. And then in 2000, we had 3.9 million males and 2.8 million females participated. So instead of having this all out in a big paragraph, we're going to store it in a nice, concise matrix. We're actually going to do 2 different ones here. Store the high school athletic participation information in matrices 1, 2, M1 and M2. So here's M1. So we just have to basically match up the information. So in 1980, how many males were there? Just go back up to the paragraph. We have 3.5 million. So I'm just going to put in the decimals here, 3.5. And you can just keep going. As we read it, we could probably fill it in. 1.9 million females were in 1980 as well, so you do 1.9. The next sentence says 10 years later, so 1990, we have 3.4 million males, 1.9 again million females. So it actually decreased a little bit for the males. Females stay the same. And then the last sentence here, we have 3.9 million males. So a huge jump in both females and males. Mostly the females go up to 2,000, or in 2000 went up to 2.8 million. So that's just a nice, concise way of storing the information that was in this paragraph. So I already went through it all. So it could be written this way, with the years being your rows and your gender being the columns. And then you can also switch it around. So what if we had it this way? That'd be fine, just as fine as well. We can just have the information displayed a little differently. Otherwise, we can just basically copy everything over. So we can do 3.5, right? 3.4 displays the same kind of information. 3.9. And then 1.9, 1.9, and 2.8. All right, so what are the dimensions of M1? This is where they might be a little different here. So we have 1, 2, 3 rows. So it's a 3 by 2 column. And then M2 would be 1, 2 rows by 1, 2, 3 columns. So now the question is, are these matrices equal? Well, even though they display the same information, they actually are not considered equal. No. In order to actually answer this question and understand why they're not equal, we have to go to a definition of what makes them equal. So that's what the next part is. Equal matrices. So matrices are equal if and only if they have to have the same. What do you think they have to have the same? They already know they have the same information in here, but what has to be the same is right down here. And that's what we don't have the same of. They have to have the same dimensions, and so if they have the same dimensions, then their corresponding elements, the individual pieces, objects in the actual matrix, have to also be equal. So not only do they have to have the same dimensions, which they don't here. These are not the same. 3 by 2 is not the same as a 2 by 3, but they would also have the same information, which they do have the same information, but they're not the same dimension. So we're just going to do some filling in the blanks to make equal matrices. Find the missing information to make the matrices equal. Not too difficult. So if this position here is -4, that means over here is -4. If this is 3, that's 3. And then reading from the other side, if this is 0, that's 0. We're just making them the same. Not that difficult, hopefully. We'll go in this blank here. That would be 0. And then this blank would be 2. And then going down the next row, we have what? -4. Going over here, 6. Just copying them across, -12. The last row, we need 98 and 45. And 1 on the other side. That's what makes them equal. Same dimensions, as you can see. These are both a 2 by 2. And these are 3 by 3s. They don't have to be the exact same numbers, 3 by 3, 2 by 2s. It could be like 2 1 by 3s. It doesn't matter. But they are the same, exactly equal. All right, we have like 1 or 2 more concepts, I think. And then we'll be done. So you can also have XY points in a matrix. So points and polygons can be represented by matrices. If you have an ordered pair XY, they just write that vertically as a matrix XY like this. So it's a 2 by 1 matrix, and they call that specifically a point matrix, as in it makes a point, like on a coordinate plane. So we're going to practice writing these ordered pairs XY as a point matrix. For example 6, write the ordered pairs as a point matrix. We're just going to rewrite this. Instead of having 3, 4 horizontally, we're going to write it vertically. So you practice writing your little brackets. And then X has to go first, and then it's Y. So if we practice that, it goes XY. So it just goes 3. Oops, I didn't mean to do that. 3, give a little space, 4. Part B, do our little brackets. Again, it goes XY. So the top number has to be X, -4, 1. And then the last one, 0, 2. And that's it. One more example, I believe. Yep. So these can actually be put into one bigger matrix, and we can consider this to be an actual polygon. So we're going to actually draw all these points here and then connect them together. So again, so you remember, it goes X and then Y. And then these will be our individual points, right? So if you want to write these out, you could say we have one point that's 3, 1. We have 0, 7. We have -5, 5. Now you don't have to write these out. You could just figure out how to plot them. Then we have -1, -1. Okay, so let's plot these out. We have 3, 1. So that would be here. We have 0, 7, which is up top here. -5 and 5, which would be here. And -1, -1. It's down here. And then we're going to connect them in that order from 3, 1 on. So 3, 1 would draw a line from 0 to 7 here. I'm not going to be able to draw them that straight, that's for sure. 0, 7 to -5, -5 would be here. And then we're going to go down to -1, -1. And then we connect it back. So it makes a polygon. So we completed it. Draw a polygon to describe the matrix below. And that's pretty much it for matrices so far. That's all for 4.1. You can finish up the rest of it, which covers everything we just did. The only other thing is one of the problems is that you're actually making your own 2x5 matrix. So in number 4, you have to make a 2x5. So make sure you leave enough space. You have to have 2 rows, and that means 1, 2, 3, 4, 5 columns. And you'll be doing the polygon penta. So for each letter, you're going to be making a point. So you'll start with P, because that's what P is in penta, and then you'll go around P, E, N, T, A, and that will be your points here, and so on. That might be the only thing that might be a little tricky. Otherwise, everything else seems to be hopefully fairly easy to do. And that will be the end of 4.1.